In this demonstration, I will show you how to develop a buffer overflow, particularly a stack overflow. I am doing this demo on a Linux system. That is a personal preference. There is no other reason than that. I happen to have a Linux system readily available. I know it has the compilers installed I need, and that's why I'm using this. This same technique would work on any other operating system. It could be a Mac, it could be Windows, it doesn't matter. Let's start by exploring a vulnerable piece of code. The example I'm going to work on with you is written in the C programming language. Buffer overflows are easiest to accomplish when you have a language that does not do boundary checking on arrays or buffers, or even strong type checking, and C meets that. So we're going to explore our vulnerable program, vulnerable.c. It's a very short program, and as we trace its execution, we see that in C a program starts with the main function, and in this case the main function just prints out two strings, calls a function foo, prints out another string, and then returns without doing a whole lot. The buffer overflow magic happens in the foo function, where when we look at it, we define a function. Within that function, we create a character buffer of 150 characters at most, and then we interact with the user by printing a brief string that says enter your username, reading from the buffer, the user, what the name is, and placing it into this buffer, and then telling that person, welcome to this application. The buffer overflow happens here. In this particular line, we're going to assume that the user never puts in more than the buffer can hold. And that obviously is not a great assumption to make. The getAs function is deprecated, it should never be used, but in this particular case it serves our purpose. But before we can start developing the exploit, we need to set up our environment. Most modern Linux systems do come with protections against these stack smashing attacks, even though those preventions can be bypassed. So we're just going to turn them off. That makes the example a lot easier to understand. Know that when they are active, the exploit is harder, but still feasible. Okay. In order to be able to do this, we need to be root, because we need to change a kernel setting. Specifically, what we're going to do is turn off the value 0 into proc sys kernel randomize va space. No, sorry, not random, randomize va space. Randomize va space will randomize the address space that the program has. So if I don't randomize, the same variable will always be stored at the same memory address. That's not something we want to happen, because that makes it predictable, and because it's predictable, it becomes easily exploitable. For now, we're going to turn off that randomization because it makes our example easier to understand. The other thing we need to do is enable core dumps, and we do that with unlimit -c unlimited. So these two settings, the first setting that you need to execute as root randomizes, turns off the randomize va space protection. The second protection we need to do is turn on core dumps, so we have something to analyze when our program starts crashing. Good. So again, we have our vulnerable program. Obviously, a C program needs to be compiled before we can run it. And again, here we have to tell the compiler to be purposefully insecure for this to work. And even at that, it will throw us a warning that we're going to happily ignore. So we're going to compile and turn off the stack protector option. We don't want that, even though under normal circumstances we would. Again, it can be bypassed, but for the sake of this example, it's easier to explain what's going on with the protection turned off. We also want the stack to be executable. Normally, code that is located on the stack, which is where our buffer will be, cannot be executed on modern C compilers and operating systems. Here we say yes, it can. What we want to do is include debugging symbols, that's G. I want to suppress all warnings, and I want to put my output in a vulnerable, and the program I'm compiling is vulnerable.c. So these options we're just gonna take for magic. Now, notice that the compiler is telling me I am using the getS function, it is dangerous, and it should not be used. So it is pretty obvious what this error message means, what this warning means, but that's all it is. It's a warning. It did not prevent me from building the software. The software, the vulnerable executable, is still there. It's 19 kilobytes-ish, but it did compile. The basic premise of a Stack Overflow is that we have a local variable that we overflow, that we put more data in that it can hold, and that by trying to figure out exactly how much data we're going to put in, we can overwrite the instruction pointer that tells the program to where is the next instruction you're going to execute, and that instruction is going to be in our buffer. So what we want to do is make sure that we can overwrite that instruction pointer. The way to do this is by fuzzing, by just dumping a whole bunch of data into our program and see if it crashes. If it crashes, that means that we've overwritten the instruction pointer with an address to which we don't have access, and we'll get a segmentation fault, hopefully with a core dump that we can analyze. So we can easily do that, just writing a quick Python program that will print a whole bunch of output, say 500 characters. See, by itself it does this, but what we're going to do is take this output and use it as input to our vulnerable system. And you see the program executing, calling a buffer overflow exploit. This was in the main function. This was in the main function. This was the, over here, the full function, and this is where it crashes. Right? So it tells me segmentation fault, core dumped. I'm trying to access memory that isn't mine. The operating system is not going to allow that, and is going to terminate my program. This is good news. This is what we were hoping for. We can try to repeat this again and again, and what we see is that our program crashes reliably. In any case, anytime that we're debugging or maybe even exploit development, we want to make sure that we have a repeatable situation. So just doing it once isn't good enough. It could have been an accident. Unlikely, but it could have been. Save yourself the headache down the road. Make sure that whatever you do, you can reproduce. In this case, 3 out of 3, that's good enough for me. Now, you see that when we crashed, it said segmentation fault core dumped. The core is a file that represents the exact state of my program, including the entire state of the memory used by that program, including all the registers, right before the operating system killed it. So that has all the debug information I need. Because I compiled my executable with a -G option, all the debug symbols are included too, which makes it a little easier. Not necessary, but it's very helpful. So let's take a look. What we want to do is run our debugger, GDB. We have our vulnerable program, that's the one we want to debug, and we want to do that in the context of this core. And a whole bunch of stuff. I can inspect the registers, so the registers of the CPU as the program was killed, and we see a whole bunch of values that seemingly look random, but I say seemingly for a reason, and the reason is here. A range of the same value that repeats and continues to repeat, at least apparently, is more than just a coincidence. I see the hex value 41, 41, 41. That's not a coincidence, and I'll show you why. because remember what we put in the input, right? We put all these A's in here. It turns out the ASCII value, the ordinal value in the hexadecimal alphabet of the uppercase letter E is right here, hex 41. So what we see there in that register is not just a sequence of 41s, it is really a sequence of numbers, letters A, and I have put those there. So back to the registers, register. So it means that I've overwritten something, RBP. I can also quickly check to see what my RSP register contains, and the same thing there. I have a whole bunch of 41, 41, 41 values. This is all good news. That means that we were able to inject something into these buffers that started overwriting memory addresses that controlled our execution, and that's exactly what we're trying to accomplish. Now, let's take a look again. Back to my 500 A's that we're putting in. And the question, of course, is which one of these A's caused the actual segmentation fault? In other words, which of these, in this case 8 A's, because I have a 64-bit operating system here, were interpreted as being a memory address that we didn't have access to? And the question is, we don't really know that, so we have to find out. One way would be through trial and error, by constantly, in this case, reducing the number of A's until my program stops crashing. But that's kind of labor intensive. We have a better tool for that. That better tool is part of the Metasploit Framework, and it's called MSF Pattern Create. What we're going to do is create a pattern of 500 characters long. Takes a while. Metasploit Framework and its utilities are written in Ruby, and it takes a while to launch. But what we see now is that we have a whole bunch of values and they never repeat. So for example, if somewhere in my memory I'm going to find this sequence, I know exactly where in this stream of characters this sequence occurs. So try that. I'm going to create the sequence again, but now not to look at. We're going to give it to our vulnerable software. There we go. Segmentation fault core dumped. I forgot to tell you one thing. This core file is here. Core. April 12th, 10:38. Cores will not be overwritten, which means that if you want a new core, you have to remove the old one first. So rm core, and we'll run our program again. Now we have a new core. So same thing again, gdb, my vulnerable program, and the core. And let's take a look in that RSP thing again. Now we find these values. That's not the same 41, 41, 41, 41 that we found there before. Now we have something new. Now I could go back to my ASCII table. Oops, one step too far. I could go back to my ASCII table. Paste. Do I have a paste option here? XRSP. I could go to my ASCII table and say, okay, what's 41 again? Well, that's uppercase A. What is 36 and 66? Well, let's see. And ASCII 36. 36, that's around here. So we had uppercase A, number 6, then we had 66. Number 66 is B, so we had uppercase A, number 6, uppercase B. That's very laborious, but the Metasploit people were nice enough to say, given that pattern you just created, query, offset, sorry, at what memory address, what offset in my stream, copy paste, do I find the sequence as is. I don't have to worry about translating it to ASCII first. And what it's telling me is that at exactly 168 bytes in, that's when I started overriding my instruction pointers. which means that I need to create a buffer that is exactly 168 bytes so that I can then put in the instruction pointer that I'm looking for. So that's good information to have. We should probably write that down somewhere. So let's create a new window. New window, notes. Buffer size equals, let's say here, 168. So that's the value we want to remember. That's how big our buffer needs to be before we can overwrite the return pointer. And that's not how you spell that is. We do have enough information that we can start thinking about how to create a buffer overflow for this particular vulnerability. So we're going to write a quick script. I prefer to use the Python language just because Python is an easy one. So let's do some preamble stuff, and we're going to need the sys module in a second. We know that our buffer size, the total size of bytes that we need to fill, was, what did our note say? Okay, notes 168 characters. So let's write that down. An exploit like this typically consists of 4 main parts. It starts with a knob sled, a whole bunch of repeated no operation instructions in machine code. And for now, we're just going to make, say, started with 16 of those. Why 16? Not 16. It doesn't really matter. After that, my actual exploit code will happen. That is the malicious malware that I want to execute if I'm successful at doing this. And after that, I'm going to write, padding. Enough data, it doesn't matter what's there because it will never get executed. It's just data to get to 168. So that is 168 minus that 16 minus the length of the buffer. And that's how much data I need to pad with. What I really should do is not call it padding, but pad size to be consistent. Good, so now that I have this set up, I can say, well, my knob sled is that knob operation x90. How often? Well, knob size, that often. I have my buffer already, or I will have that by the time I'm ready to create my final exploit. And I can create my padding, because my padding can be anything. In this case, I want it to be something that I can recognize when I'm looking in the debugger, so I'm just going to create the uppercase B, repeating hex 42. And I need a return address. Return address. That's what I'm going to execute. I don't know what it is yet. So for now, 2, 3, 4, 5, 6, 7, 8. I'm just going to put in a 64-bit placeholder that as I work through my exploit, I will refine and I'll get back to when I can. The last start is that I can now write my exploit buffer, beginning with the sled, followed by the buffer, followed by the padding, which is followed by the return address. That's going to be the basic format of my exploit. So at this point, I need to find what my exploit code is, and I need to fine-tune my return address. Everything else should be in place. When I run this, I can just go Python create buffer. There's some binary code in here, so we'll run it through a hex. Oh, made a mistake. Oh. It's called buff, not buffer. This is what my exploit for the time being looks like. Now, of course, like I said, I'll have to change some of the spanning to the exploit code, all these B's, but we'll take care of that, and we have to put the actual C's, the return address value in. But this is a buffer. This is the exact buffer that should work. And before we go any further, we should test that. So that would mean that we're going to create my buffer. Oh, remove my core first. Remove the core. I'm going to create my buffer, and I'm going to feed that to my vulnerable code. I accidentally closed my window, so I have to turn that back on. U limit -c unlimited. And here we go. 4 dumped. Back to GDB, from core. And I'm really only interested in what's in that RSP now. And here you see 4.3, 4.3, 4.3, etc. And 4.3 is exactly the hex representation of the uppercase C, which means that at this point I have correctly overwritten the address that I need to overwrite. I haven't had the right value in there yet, but at least I know that my buffer is of the correct size and at least of the right composition. The return address that I'm looking for would be the start of the buffer that I'm injecting, because that's where my code is going to be. Which means that I need to figure out what the bottom of the stack is right before I inject my malicious code, because that's where my code is going to be. I'm going to quietly start my vulnerable program, and I'm going to disassemble my function, my full function, because that helps me recognize right here in this line, let me highlight it, when that getS function is called, the vulnerable function, the function that causes the buffer overflow. I'm just going to set a breakpoint there. I'm using this syntax: break space star space name of the function and the offset. And then we'll go to run. Excellent. My breakpoint kicked in, and I want to know what now the value of my RSP function, and it's this number here. And this is not going to be my final version. I'll have to fine-tune this a little bit as I develop my exploit, because right now I'm running in the debugger, which affects the composition of memory a little bit. So once I'm not running in the debugger, I'll probably have to tinker with that a little bit to get it to where I want it to be. But for now, we're going to just put that value in. And I'm starting to put it in as comment. And the reason for that is that memory addresses in an Intel architecture are flipped the other way around. And they need to be 64 bits long, which means that in this particular case, the most significant byte, which is 7F, that gets listed last, and the least significant bit, which is not, as you would expect, 70, but it will be 00, comes first. And why is it 00? Because I need to get to 8 bytes, 64 bits. 1, 2, 3, 4, 5, 6. That means I'm going to add 7 and 8 to it. That's the value I want to end up with in my return address. That needs to be literal values so that the CPU can interpret it correctly. So 70, E0, E0, FF, FF, XFF, XFF, X7F. That's the endianness. Okay, that's it. So we have a preliminary return pointer in there now. Which means up again. Okay, let's take a look at our exploit code. What we have been able to fill in so far is the buffer size. We have taken a pretty good guess as to what our return address will be in the end. We know how big the knob sled will be, but we didn't create a payload yet. What is the malware that we're going to be executing if this buffer overflow is correct? So we have a tool for that, part of the Metasploit Framework again. It's called MSF Venom. MSF Venom can list out a whole bunch of payloads it can create for us. And we know that we're running on a 64-bit Linux system, so we can just filter out all its possible options just to those. And we'll see there's quite a few options at our disposal. Now, remember, we only have 168 bytes to play with. Some of those bytes are going to be used for the knob sled. Some of them are going to be used for padding. And even though the knob sled and the padding are kind of optional, they are very useful when it comes to debugging. But it also means that our exploit code itself can be limited in size. It needs to fit within that buffer. Turns out that's not really a problem. For example, let's try this one. Let's try to figure out what the machine code variation of this exploit is. And so, oh, did I copy it or not? No, I did not copy it. Oops, go back. Copy. Now I have it. MSF Venom with the payload here. And for now, I'll stop it at this. Since the payload is machine executable code, I'll run it to a hex dumper so we can see what it looks like. So this is it. But it does mean that this shell-bind TCP exploit, which will open a TCP port, and whoever connects to that TCP port will get a shell, can fit in only 86 bytes. We have 186, no, 168, whatever, enough. You see that this is also strange stuff, hard to put into a programming language. The people who made MSF Venom made that easy, but because what we're going to ask it is, can you just give me that buffer in Python format, please, so I can more easily incorporate it into my own program. And of course they say, sure we can. So, copy, and we go create buffer. And so where we had this originally, now we're going to just paste this whole thing in. Just straight through, no editing, no nothing. Because the padding size was already determined by the length of the buffer, it now dynamically adjusts itself. It also means that this part here dynamically adjusts itself, and that we now have a new exploit code to work off. My buffer has been updated. I can take another look at it. But you'll see that this is now recognizable as my knob sled, one row. That's why I chose 16 values. And here is that executable bytecode. Here is my padding. And here at the end is my return address. So I don't expect this to work yet because we haven't fine-tuned this return address yet, but we're getting closer. Take a look. Let's see what happens when we take our custom malware and we feed it to our vulnerable program. We have a core dump. And we clean up the old core and recreate a new one so we can analyze it. GDB vuln core. What's in RSP? Not the value we put there, and that's because we're off. We're not our buffer isn't starting at the right place. It's the right size, but it's not starting at the right place. So let's go take a look at, say, at 100 bytes at a time in hex notation. And let's start, say, 100 bytes before that RSP value. When we look at that, we immediately recognize, hopefully at least, that this here is our padding, which means that right before our padding sits our exploitable code, and right before our exploitable code should sit our knob sled, and that's where we want to start the execution. So we need to go back a little further. 150 is still not enough. See, this is still part of the machine executable code. So we'll go back 200. See if we get there then. And here we find our knob sled. So we're going to look for this address here. OX7F, a whole bunch of Fs ending with E0B0. Let's add that to the notes, so that I don't have to try and remember that. I'll copy it first. Copy. Paste. Get there in a second. But at this point I can drop out of my debugger. I don't need it for now. Let me clean up the core ahead of time. And we're going to update our buffer with the correct return address, which is not 7F, FF, FL, F, etc. Oh, and also did this the wrong way, because what I should have done wouldn't have worked to begin with. So do this. Should not have been at the end here, but they should have been at the end here. That was a mistake on my part. It's okay, we needed to fine-tune it anyway. There you go. Okay. So what do we have? 0, 0, 0, 0, 7F, a whole bunch of Fs, E0. That's the same thing as we have E0 over here. And then last byte is B0, B as in Bravo. We had 70 there, so we're just going to replace 70 with B0. And now, hopefully, things are going to work. So let's test that. We're going to take our create buffer and we're going to feed it to our vulnerable software. And notice that there is a difference in behavior now. What is not happening, but that was happening before, is a core dump. It means that my program is still executing. And if we are very lucky, my program is actually executing the payload that we gave it. What did we tell the payload to do? We said open a TCP socket. The way to list open socket is to use the SS, the socket status. I'm looking for a socket that is listening on a TCP port using IP version 4, and I don't need any domain resolution. And we see that there actually is one process running that is listening on TCP port 4444 on all interfaces. Well, let's see what happens. We're going to connect with netcat. Let's have it be a little verbose. What are we connecting to? Localhost 44444. And you see that we are connected. We're not seeing any output, but that's expected because we don't actually have a terminal. What we can do is interact with the terminal. Who is online? Who am I? What's in the file system? Where am I in the file system? All of that works. We don't see anything here because this buffer overflow is still executing. But what we do see is once I exit from my shell, my exploited shell, my program up here also exits because my executable code then finishes. And we have successfully created a buffer overflow. Which means that now, instead of printing my values back, could be anything, every time I run this, I have a backdoor on my system that I can connect to and have a full interactive shell ready and waiting for me.